Is Safara, and today I'm going to serve as the moderator for our parallel session today. Before we begin our parallel session today, I would like to explain about the rules first, and after that, I'm going to check the attendance first to make sure that all presenters already here. For the preparations before we begin our parallel session, please don't forget to rename your username with the following format: room number, paper ID, and full name. Please also use the virtual background provided by the ICADEIS 2026 committee. During the presentation, each presenter will have 10 minutes for the presentation and 5 minutes for Q&A sessions. The question can be from the other participants, both attendees or the other presenter. We will also set a timer so you can see how much time that you still have left. Please turn on your camera and microphone while presenting, and kindly mute your microphone when you are not speaking. After you already finish your presentation, please do not leave the room yet, because at the end of the presentation, we will have a photo taken together as our documentation for the parallel session today. Now I will read the sequence of the parallel sessions today. For the first presenter, we have the title Prediction of Gallstone Disease Using Interpretable, Probabilistic, and Deep Learning Model for Tabular Data, and will be presented by Joel Edward Arunglabi from University Bina Nusantara University. I think for the presenter already here. I already see you. And then for the second participants here, the title of the presentation is Machine Learning-Based Classification of Toddler Nutritional Status, Analysis of Feature Importance and Approach to Data Imbalance. It will be presented by I Gede Made Ari Ananta from Telkom University. I think I can already see you here. For the third participants, there will be, the title is an IoT-enabled ESP32 system for collective couch detection using FFT and threshold techniques. It will be presented by M. Akilanesha and Andi Muhammad Rafan from MAN 2 Makassar. And the fourth presenter, the title is Topic Modeling of Parent Trigger Mental Health Complaints on Indonesian Social Media Using Latent Direct Like Allocation, will be presented by Muhammad Handrahak from Telkom University. I think I also already can see you. Okay, so because all the presenters are already here today, for the first presenter, Mr. Joel, you can start your presentation and you have 10 minutes to do your presentation. The floor is yours.
Okay, thank you. Yes. I will share screen first. Can you hear my voice clear?
Yes, your voice is clear.
Okay. So good afternoon, everybody. My name is Joel Edward Arunglabi, and today I'm going to represent my colleagues to present our research paper with title Prediction of Gallstone Disease Using Interpretable Probabilistic and Deep Learning Models for Tabular Data. So here are the content lists that I will present. The first one is introduction. In introduction, I will explain on why gallstone disease is concerning and what are the current research on predicting gallstone disease and the gap that our paper fill. And then the second one is method. In method, I will explain what approaches or method that we took to predict the gallstone disease. And then for result and discussion, I will show you the result of our research. And then for the conclusion, I will show the conclusion of our research. We will begin with introduction. So why gallstone disease is concerning? It's because it is a widespread global health concern that affecting roughly 80% of population in Europe and America. And if we look at the cost, it took exceed 6.5 billion US dollar in the US itself. And currently, the tool that commonly used is called ultrasound, but it is very depend on the operator skill. That's why in some cases, the result is ambiguous. And for the current research, in other paper, they are already explored with AI approaches, but they focus only the accuracy and the model performance. That's why me and my colleague's research paper is going to fill the gap that not only focusing on the model performance, but also the interpretability. Since in medical settings, if a doctor using a tool to help make their decision, they have to know why the tool decide that decision, not only black box. And then we go into the methods. Here we are using data set from Ankara VM Medical Park Hospital. The data set contains of 390 patients and the 161 diagnosed with gallstone disease, and it has 38 features. For data pre-processing, we use standardization. We use standard scalar with z-score normalization. It helps us improve data consistency and prevent the feature imbalance. And then we use feature selection. The method we use is recursive feature elimination with random forest as a model to reduce the 38 features into the 18 most relevant features. And then we also prevent the data leakage by using standardization and RFA only on the training data within the cross-validation pipeline. And for the models, we use 5 models here. The first one is NGBoost, natural gradient boosting, and the second one is XGBoost, extreme gradient boosting, and then TAP-PFN, TAP transformer, and explainer boosting machine or EBM. So we also do hyperparameter tuning here. We use grid search CV with 5-fold cross-validation. It helps us to identify the optimal model parameters. And also the model parameters was evaluated using a repeated hold-out validation with different random seed value. And for the TAP-PFN models was excluded in the hyperparameter tuning because it is a pre-trained fixed architecture. So we cannot change. And then for the results, here we have the 3 best performance. The first one is EBM. It has balanced performance across the 3 metrics: sensitivity, specificity, and ROC-OC. And then the second one is TAP-PFN. It is good in terms of the specificity and ROC-OC, and then XGBoost, it is good in the sensitivity. We also do pairwise will solve Cosson tests across 10 runs, and it is revealed that TAPFN is significantly outperform EBM in ROCOC and XGBoost. It has superior sensitivity. So pairwise Wilcoxon Wilcoxon is helping us to check if the different performance is really significant or not. And also we also do the feature analysis from the interpretability. And on the interpretability that have done by 3 models, XGBoost, TAPFN, and EBM, they showing strong consensus that CRP was the top predictor of gallstone disease. And then we have vitamin D ranked second, and then obesity, bone mass, and intracellular water in behind. And also, we also do uncertainty and calibration analysis on NGBoost. It helps us to know how confident the model on making decision or predicting the disease. So for the conclusion here, the first one, XGBoost achieved the highest sensitivity, and then TAPFN achieved the highest specificity, and EBM show the most balanced overall performance. And then for the conclusion too, from the interpretability methods, it showed that CRP was the most important predictor across top performing models. And then vitamin D and obesity were also highly influential on predicting the gallstone. And then we also know that integrating the interpretability methods into the model did not significantly compromise the predictive performance. And for the future research, we aim to use larger and multi-center data set, and then we also want to conduct clinical validation studies to make sure. And I think that's all from our research paper and from my presentation. Here are the references that we use when building the research paper.
Thank you so much, Mr. Joel, for an insightful presentation today. From the participants or audiences, do you have any question to Mr. Joel? You can raise your hand or you can ask in the chat box here. Okay, while we're waiting for the audiences to have any question, maybe I will ask the first question to Mr. Joel. I wonder, is there any specific data related to Gelston disease, but in Indonesia? I mean, like previously in the introduction, you already mentioned that if it is related to the US and European data, but I wonder, have you done the benchmark for the case in Indonesia?
Okay, thank you for the question. Currently, we haven't explored in the Indonesian data. Currently, we use the US and Europe since it has the best technology in there, and we currently only found the data on Europe and America only. So we haven't get the consensus or data for the Indonesia.
Okay, thank you so much for your answer. And I also would like to ask about the data set you use in the research. How did you gain the data set?
So we get the data set from, it was from repository. It's machine learning repository called Uchi, and it's quite popular. So that's why we pick the dataset because it has reputation that the dataset uh, it's is true, not a dummy data.
Okay, and it will be the last question for today. What kind of problems did you face during the research, and how did you manage to solve it?
Okay, so we have problem because the dataset currently is small, only 319 patient, and the first one we think it will be overfitting. So we use repeated holdout and we run around 10 times to make sure the overfitting will not hit. So if if we only run once, there is more potential that it will overfitting. That's why we use repeated holdout and we run the model 10 times. That's how we solve it.
Okay, thank you so much, Mr. Joel, for your answer and for your presentation. That concludes the presentation from Mr. Joel, and we would like to proceed uh, to the next participants. For the next participants, it will be presented by Igede Made Ari Ananta.
Yes, I'm here.
Okay, you can share your screen and you can start the presentation if you're already ready.
I'm sorry because I think Joel still shares the screen, so I can share the screen.
Okay, sorry, sorry.
All right. So, yeah, okay. Um, yeah. Can you see and hear me properly? Yeah.
I can hear you clearly and your presentation is already shown here.
Yeah. Okay. Okay. Hello everyone, my name is Gede Made Ariananta and I'm from Telkom University. Today I will present our research about using machine learning to classify toddler nutritional status, and the title of this research is machine learning based classification of toddler nutritional status, analytic feature importance and approach data imbalance. So, in this presentation, I will explain about the introduction and background, problem statement and research gap, data set overview, methodology, result and, and discussion, sharp feature importance, and conclusion and future work. And first, I will explain about the introduction. Nah, child malnutrition is still major problem around the world. According to World Health Organization, 149 million children under 5 are stunted and 45 million children experience wasting. This condition can affect physical growth, cognitive development, and future quality of life. In Indonesia, the situation is also serious based on the 2024 National Nutrition Survey. This number is still above the government target, which is 14.2% by the year of 2029. The location of our study is Astana Anyar, Bandung City. Around 60% of the door is standard. And another challenge is that Posyandu health workers still use manual method to record and analyze data. As the result, the process becomes slow and children at risk may not be detected early. So this is the research gap of the research. So after reviewing previous study, we found three main problems. First, many study only use binary classification such as stunted and or not stunted. In reality, nutrition status has several categories based on WHO categories or standards. Second, many studies use a secondary dataset from sources like Kaggle, IVLS. So this dataset may not fully represent real community condition. Third, important variable record at Posyandu, such as vaccination history, feeding habits, and certain sanitation condition are not often included in the model. So to solve this problem, our research use real Posyandu data, multi-class classification, and sharp analysis to provide more interpretable result. So this is our data set. We collect about 876 record from Posyandu asalnya in Bandung City. We analyzed three WHO in nutrition indicator such as height for AIDS, weight for AIDS. And the dataset has a strong class imbalance, so you can see at the bar chart visualization on the slide. We start with 45 feature, and after feature selection, we use 33 feature. This include anthropometric measurement, birth history, feeding habits, vaccination record, sanitation, and maternal mental health. Okay, this is about the methodology. So, our research framework consists of 6 main stages. The process starts from data collection and data understanding, followed by processing, handling class imbalance, model training with hyperparameter tuning, evaluation with statistical significant testing, and finally sharp feature importance analysis. To maintain the data integrity and prevent data leakage, all processing steps such as encoding, scaling, resampling were fitting only on the training set before being applied to the test set. So, to handle a surf class imbalance, we systematically evaluate for resampling, such as random oversampling, smooth Tomac, and smooth ENN. An important consideration is the classes with the very small size may produce noisy synthetic data during the interpolation. Because of this, comparing of all four method becomes very important. So this is about the modeling and evaluation. We benchmark 6 machine learning model, logistic regression, and decision tree were used as a baseline model without tuning. Our 4 example models, namely random forest, XGBoost, LabGBM, and CatBoost, underwent 2 optimization stages, like a threshold calibration followed by Bayesian hyperparameter optimization. For evaluation, we prioritize macro F1 score as the main metric to ensure the balanced performance across all classes. We also use a stratified key cross-validation with 5-fold and applied the Wilkinson side rank test with a significant level below 0.05. So here the result. For weight for head, XGBoost with random oversampling achieved the best macro F1 score at the 62.48%. This result better than a smooth and the other sampling like smooth ENN produced the lowest performance. For weight for apes, XGBoost with random over sampling also achieved the best result at 63.60%. Interestingly, like GBM with our resampling also performed quite well. For head for edge, the result was different. Like GBM using the original data with upper sampling achieved the best performance at the 49.44%. When the smooth ENN was applied, the performance dropped significantly. This finding shows that the simple resampling method like random oversampling may work better under the extreme class imbalance condition. In some case, the original dataset may even produce the best result. So is about the assemble versus baseline and the statistical test. For weight for head, XG boost achieved 62.48%, while dysentery achieved for 52.27%. For weight for edge, XG boost achieved a 63.60% compared to 48.13% from dysentery. For head for edge, like GBM achieved 49.44%, while decision tree achieved 41.41%. We also performed the Wilcoxon statistical test for weight for edge. The improvement was statistically significant with a p-value 0.031 and a very large effect size. For the other indicator, the effect size were also large even though the p-value were slightly above the threshold. Next is about the sub feature importance. So sub help us understand why the model makes a certain prediction. This is important because health worker needs interpretable result. For weight for head, the most important feature were logarithm of child BMI, weight velocity by age, and log weight for head ratio. For weight for age, the important feature were also related to BMI and weight growth. For head for age, the most important feature was weight for head interaction. This suggests that chronic stunting is more related to long-term growth pattern. Another important finding is that the social economic factor and birth-related factor appear consistently across all indicators. This means malnutrition is influenced by only by food intake, but also family condition and birth history. So it is a conclusion. To conclude, assemble models such as XGBoost and like GPM successfully classified to learn nutritional status using real portion data, and they perform better than the baseline model. We also found that simple resampling methods like random oversampling can work better than more complex method under severe class imbalance condition. In addition, sub-analysis show that malnutrition influenced by multiple factors, including social, economic, and perinatal condition. For future work, we hope to expand the dataset to more region, integrate the system with digital patient record, and develop a mobile application for health worker. We hope this research can support better decision making in community healthcare. So, thank you for your attention. Yeah. So,
Okay, thank you so much for your presentation. Now we will open the Q&A session for the participants who would like to ask. Okay, I think we already have the first question. The first question maybe from Mr. Muhammad Yoga first.
Thank you, moderator, for the opportunity. My name is Muhammad Yoga from Telkom University. Your study is actually very close to mine. I work on the same problem set, but I extend the prediction target from nutritional status classification toward direct intervention recommendation. So in a way, your diagnostic output is exactly where my perspective framework begins. My question is about your finding that ROS, random oversampling, which is very simple duplication method, outperforms MOTE, which is a more sophisticated synthetic method. This seems counterintuitive because in most literature, SMOTE is considered superior for imbalance data. Can you explain why this happened in your study, and does this mean we should stop using SMOTE for health and data classification? Thank you.
Okay, so I will answer directly. Thank you for the question. Yes, you are right. This research surprised us at first, but it is one of our most important findings. The main reason is that our small class have a very few data, right? So, for example, for head for edge, same category have fewer than 15 samples. In this situation, small cannot work well. Smooth creates new data by connecting close data points. But when you only have 2 or 50 samples, this point don't represent the real situation. So Smooth create a fake data that is incorrect and act like noise. And then random oversampling, on the other hand, just copies the real sample that already exists. It does not create anything new. Because of this model still learn from the real and true data pattern, even if they are repeated. For smooth ENN, the problem is even worse. It creates a fake data and also deletes important data points near the borders. When you have a few samples, deleting even a few points make it impossible for the model to learn about those real classes. And to answer your second question, we are not saying smooth is always bad. Smooth works well if you have enough sample, like 15 or more, I think, or and our point is specific. For small community, health data like Posyandu data, simpler methods are safer. We recommend testing multiple method instead of assuming smooth is always the best. I think that's my answer for Mr. Muhammad Yoga. Yeah.
Okay, thank you so much. I think we still have the second question from Miss Hilya. You can ask directly.
Thank you, moderator, for the time. So my name is Celia. I'm from Telkom University. So your framework was sound very promising as a decision support tool for Posyandu health worker. But I want to ask about partial deployment. Posyandu health worker are mostly volunteers, called by cadre, right? Who may have limited education and limited access to the technology. Some operate in area with no internet connection, given this real world constraint. How realistic is it to actually deploy your machine learning model at the Posyandu level? And what happens if the model makes the wrong prediction? Who is the responsible for this clinical decision? Thank you.
Okay. Thank you for the question. You are right. About the challenge, Posyandu, like a Kader Posyandu, I will say it, are the volunteer, right? But they are not a computer expert. Many use basic smartphone operation, and some don't have internet. So we must design the tool or for them, for not for the data scientist, right? So we plan our mobile apps follow 3 simple idea. First, it works on offline. The model live inside the phone, so it can check risk without internet. The data will save and synchronize later when the internet is available. Second is very simple. The app is not show complex score or sub chart. It will use simple traffic light colors, green or for formal, yeah, normal, I think, yeah, sorry, yellow for warning and red for high risk. With one say sentence in bahasa Indonesia. Third is only a helper tool, not a replacement for human choice. The Kader inputs the measurements. The app give suggestion, and the Kader use their own judgment to decide next steps. For wrong prediction, if they are wrong prediction, who is the responsible, right? So this is a key question. Our tools only give a recommendation, not a official medical diagnosis. We final choice always belongs to the human health worker or the doctor at Puskesmas. Yeah. We also plan to monitor the app's accuracy to see when human agree or disagree with the models, helping us to improve it over time. Yeah, I think that's my answer for Killing Nafisa.
Okay, I think that's all for the session, and we will next proceed to the next presenter since the time for Q&A session has done. So the next presenter is M. Akilanesha and Andi Muhammad. You can start your presentation.
Oh, sorry.
Okay, so I'll start my presentation. Share. Okay, so good day to the esteemed judges, open floor audience, and fellow researchers. My name is Muhammad Akilanesha Patahya.
And my name is Andi Muhammad Rafan. We are from Mandua Kota Makassar, Indonesia. Today, we are proud to present our project, an IoT-enabled ESP32 system for collective cough detection using FFT and threshold techniques.
So coughing is a major clinical warning sign for respiratory illness. In shared collective spaces, keeping track of coughing frequency can warn us of outbreaks early on. Our goal was to build a system to automate this efficiently.
To guide you through our presentation today, we have divided our talk into 4 key sections. First, the introduction to outline our system's core purpose. Secondly, the methods detailing our system architecture and the algorithms. Third, the result and discussion, highlighting our actual device readings and constraints. And finally, our conclusion and roadmap for future development.
Okay, so moving on to the introduction. So our study centers on a lightweight monitoring system powered by an ESP32 microcontroller to continuously track cough anomalies in real time. Conventional tracking relies on manual observation or self-reporting, which lacks consistency and scalability.
To fix this, our platform merges continuous sound and chest vibration monitoring directly on a compact wearable setup. By using mathematical processing tools like the fast Fourier transform and simple thresholding, the system cuts down resource overhead dramatically. Plus, with built-in Wi-Fi connectivity, data streams instantly to remote clouds, making it easy for healthcare workers to monitor patients from a safe distance.
So next up is the novelty. So novelty 1 relies in our true multimodal sensing pipeline. Most systems look only at audio waves, which pick up ambient noise, or only at motion, which misinterprets body adjustments. By pairing a microphone with an accelerometer, we validate a cough double-fold.
Novelty 2 is our implementation of lightweight FFT filtering right on the edge. Instead of using heavy, deep learning frameworks that require extensive computing power, datasets, and expensive chipsets, our system executes directly on a budget-friendly ESP32 module. This enables low-power, automated monitoring without any complex server configurations.
Okay, moving on to the methods. Our methodology breaks down into 3 distinct layers. First one is the system architecture. In this stage, we employ the MAX 9814 audio sensor to capture acoustic pressure waves, while the MPU 6050 accelerometer tracks physical muscle recoil around triaxial planes. Both dump continuous streams into our Wi-Fi enabled ESP32. Next up are data analysis. Sound waveforms are broken down using a discrete Fourier transform equation that converts time audio frames into clear frequency bins.
Simultaneously, to calculate absolute muscle impact independent of the user's initial orientation, we compute the total acceleration factor magnitude Fm using the formula Fm equals the square root of acceleration x squared plus acceleration y squared plus acceleration z squared. And then thirdly, the testing scenario, we deployed our device during a continuous 20-minute window to rigorously log data across various cough intensities and ambient distractions.
Now, result and discussions. So let's review the practical insights from our setup. So synergy is vital here. Sound captures high-frequency audio spikes, while the MPU 6050 verifies actual chest contraction. Together, they drastically lower false alarms caused by noisy rooms. Secondly, efficiency versus prior research. Because we use vast calculations over dense AI training loops, our processing runs with minimal delay, requiring zero expensive server setups.
This brings us to a clear engineering trade-off. While our code is lightweight, responsive, and incredibly energy efficient for long-term battery use, it does rely on static conditions, meaning it yields a slightly lower absolute accuracy when compared to heavy cloud-computed deep learning models. And then the next part is research that contains research limitations. So, honoring scientific transparency, we must address our current system limitations. Firstly, testing constraints. Our trial ran for a brief 20-minute test window. While this proves the technical concept, it doesn't showcase multi-day battery drift or active movement stability. Our dataset also needs more environmental diversity. And then secondly, the technical limitations. Our severity categorization utilizes static thresholds, sorting audio levels and acceleration forces into mild, moderate, or severe brackets. Additionally, continuous data logging relies heavily on a stable and local Wi-Fi connection.
So, to conclude our talk today, we built a fully working wearable cough detection prototype that tracks real-time data using an integrated MAX 9814 and MPU 6050 sensor array linked to an interactive web interface. During the empirical testing, our design hit an overall 95% accuracy, 93.75% precision, and a perfect 100% recall, showing it never missed a true cough event.
And our final F1 score reached 96.77% with a specificity of 80%. And moving forward, we intend to introduce adaptive TinyML models to directly on chip to replace static thresholds, scale up our testing group sizes, and fine-tune power efficiency for everyday wear.
We want to express our gratitude to the Ministry of Religious Affairs of the Republic of Indonesia, our mentors at Mandua Kota Makassar, and the Research Institute for Applied and Social Science for assisting us with this study.
We also want to express our gratitude towards Telkom University for giving us the chance to publish our paper in the event of ICADEIS 2026. So thank you for listening. We would love to open up the floor for any questions or feedback you might have.
Thank you so much for your presentation from M. Akila and Andi Muhammad. From the audiences, if you have any question that will be asked directly, you can raise your hand. Maybe I will give the first question while we're waiting the question from the participants. I wonder about the budget because previously you mentioned that this solution is budget friendly, and I would like to ask how much is the budget that you use to for this research?
So, our budget was around 250,000 for two gadgets that we made.
For two devices.
For two devices, our budget was 250,000.
Okay. And I would like to ask the next question because it is budget friendly. I wonder about the problems. Let's say if the system would like to be implemented in some industrial standard that might need like a lot of things, yeah, compared to if we do it only within small environment. What kind of problems that might happen if the system will be implemented in bigger area or bigger using higher standard?
So basically, our device is not perfected yet, so it can have false positives, so it can count something like an unusual movement and like sound waves, random sound waves to be counted as a cough. So in industrial environment, in a not controlled environment, it can cause more false positives and it can lower the accuracy of the device. But right now, the main point of our device is to use it in a controlled hospital room for a contagious disease patient, so that the nurse and the health workers can safely monitor the patient's coughing patterns within a safe distance.
Okay, thank you so much for your answer. Maybe from the audiences, if you have any questions that you would like to ask, we still have time. Okay, I think that is the end of our session today. So thank you so much for your presentation and Q&A session. Now we will move on to our last presenter today in this room, Muhammad Handraha. Are you already here?
Yes, I'm here.
Okay, so from Kila and Andi, I think you can unshare your screen so Mathandra can start to present.
Thank you.
Thank you. If you already ready, you can start your presentation.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Good afternoon, everyone. My name is Muhammad Handraha from Telkom University. So today I will present our research titled Topic Modeling of Parent-Triggered Mental Health Complaints on Indonesian Social Media Using Latent Triggered Allocation. Okay, in this introduction, we will discuss about the background of this research. So mental health issues among adolescents are increasingly becoming a concern in Indonesia. According to the National Survey on Children and Adolescent Life Experiences in 2024, around 10.36% of male adolescents and 14.03% of female adolescents aged 13 to 17 have experienced emotional abuse from parents, including verbal insults and emotional neglect. At the same time, social media platforms have become spaces where people openly express their emotion and personal experiences. With approximately 143 million active users in Indonesia, Twitter provides valuable data for understanding discussions related to parent-triggered mental health complaints. Okay, for this slide, previous studies have shown that parents frequently appear in mental health discussions, and also family pressure contributes to emotional distress. And another research also demonstrated that parent-child communication significantly affects emotional well-being. However, existing studies mainly focus on identifying mental health issues rather than exploring the underlying discussion themes. To address this gap, we use latent derivative allocation or LDA to discover hidden topics in Indonesian social media discussions. LDA was selected because it is interpretable and has proven effectiveness in topic modeling tasks. And this is our method for this research. This research follows the CRISP-DM methodology consisting of business understanding, data preparation, modeling, evaluation, and deployment. This framework provides a structured process from defining the research objective to developing a practical analytical application. Next, how do we get the data? So we get the data from using tweet harvest. We collected 9,970 Indonesian tweets, and the data covers the period from January 2024 to December 2025 and was collected using keywords related to parents such as orang tua or ortu and similar variation. And on the right side, we have the sample of the tweet. As shown in the sample of the tweet, users share experiences related to trauma, emotional distress, family conflict, and mental health issues caused by parental interaction. So next, we have optimal topic selection. So several topics configuration were tested during the modeling process, and the optimal model was determined using coherence score as the primary evaluation metric. And among the tested configuration, the model containing 8 topics achieved the best semantic coherence and was selected for further analysis. And this is the best result we have. The selected model achieved a coherence score about 0.4843 and perplexity value of 4344.8. And although some configuration produced lower perplexity values, the ectopic model provided the highest coherence score. Because coherence better reflects human interpretability, it was used as the main criterion for selecting the final model. So next we have topic clusters. Here we using intertopic distance map. Intertopic distance map demonstrated among topics located closer together indicate greater semantic similarity, while topics positioned farther apart represent more distinct themes. And as we see in the picture, topics 0, 3, 4, and 6 are from central cluster related to parental conflict, trauma, stress, and emotional distress. And topics 2 and 5 show moderate similarity to family-related and stress-related discussion. Meanwhile, topic 1 appears more isolated because of its distinctive vocabulary and context. So we have discovered topic cluster. The analysis identified 8 dominant topics. So these topics can generally be grouped into several recurring themes, including emotional exhaustion, family conflict, psychological distress, trauma, parental pressure, and emotional restraint. Overall, the results indicate that discussion about parents on social media are strongly associated with stress, depression, trauma, and emotional challenges experienced by user. Next, we go to deploy. So to demonstrate practical applicability, we develop a web-based application using Streamlit, and the application can process CSV datasets containing raw text data up to 200 megabyte, and also it automatically performs pre-processing, executes the optimized LEA model, and generates interactive visualization of topic distribution. And this deployment transfers the research model into a practical analytical tool. Last, we have conclusion. So in this conclusion, this research has successfully applied LDA to identify 8 dominant topics from 9,970 Indonesian tweets discussing parent-triggered mental health complaints. And the findings reveal recurring themes such as parental conflict, emotional distress, trauma, communication difficulties, feelings of neglect, stress, depression, and experiences of loss. And also we have a limitation of this study is the lack of reliable demographic information in Twitter data. And also LDA has limited ability to capture contextual semantics in short social media text. Therefore, future research may be explored per topic or neurotopic modeling to improve contextual understanding and topic quality. So that's all for my presentation. Thank you for your attention. I would be happy to answer any questions. Thank you.
Thank you so much for your presentation. Now we will open the Q&A session to the audiences. If you have any questions, you can raise your hand first. Maybe I will ask the first question. The first question is, what kind of problems that you face during your research and how you finally solve it?
Okay, thank you for the question, moderator. So we face in collect the data. So we have problem that we also get another language text like maybe English. So that's a lot of text we get, but I think we did like doing the remove the data about English, and also we have the like Indonesian text have slang, have abbreviation that is difficult to model to understand. So we doing some pre-processing to do that, and also we found that in this case like uh, the data is sometimes we get a duplicate data. Sometimes we have data that I think not context of mental health discussion. So we remove the data. So that's all the problem we have.
Okay, and then the next question is, what kind of opportunities that can be done in the future so this research can be implemented um, for all people, not only just within the research, but it can be helpful for general people.
Okay, as I said before in the presentation, so we found that LDA model is very hard to read the short text data. So we found that we can make the research be up with uh, using the word topic, I think, and also we we make the deploy is like as you can see is uh a Streamlit, and I think this we can implement it website, so uh, a user can uh, do some data, some typing in the if we had a data CSV or something and input the to the Streamlit, and you can find the result. So I think this opportunity.
Okay, thank you so much for the answer, Mr. Handra. So I think that would be the end of the presentation today. But before we are leaving this room, I would like to ask you to take the photo together as our documentation today. Please open your camera first before we are taking the photos. Okay, I think for Mr. Joel and Akila and Andi Muhammad, if you can open your camera before we are taking the photos together. Okay, so the assistant will help us to take the picture, 1, 2, and 3. Okay, once again, 1, 2, and 3. Okay, thank you so much, everyone. On behalf of the organizing committee of ICADEIS 2026, we are very thankful for your participation and support to submit the paper with us and present with us today. Let's see each other again next year in ICADEIS 2027. Thank you and have a nice day ahead. Good afternoon, everyone.